Hi, I'm Lindsay from StatsMedic, and in this lesson today we're looking at a chi-square test for homogeneity. The past two lessons we've been looking at chi-square tests for goodness of fit. That was our first type of chi-square test, and now today we're getting into the second type, and that's a test for homogeneity. So we have four learning targets. The first is to state appropriate hypotheses, and then to calculate expected counts, and then the chi-square statistic from there. What's different about this type of test is that we are working off of a two-way table, so from data in a two-way table, versus with chi-square goodness of fit, we were just looking at a single distribution. Next, you're going to state and check conditions, so again, random, 10%, and large counts. And then we'll calculate degrees of freedom and a p-value for that chi-square test statistic, again, based on our data from a two-way table. And then we'll put it all together to turn it into a full four-step to perform a chi-square test for homogeneity. So let's move into our notes. So this is actually one of my favorite lessons because we eat a lot of gummy bears. So what we're looking at today we have two different types of gummy bears. We have the Haribo gummy bears, and then we have Meijer brand gummy bears. Now in Michigan, Meijer is like the major grocery store we go to. So think of these as store brand gummy bears. So what we're looking at is the distribution of gummy bear color the same for Haribo gummy bears as it is for Meijer gummy bears. So we collected some data as a class, and then we're going to determine if we have convincing evidence of a difference. So all of this data filled in the table, this is my actual class data from when I did this lesson last year. So if you could go ahead and take a moment and fill in all of that data onto your notes. And then after you've done that, I'd like you to work through questions 2 through 4. So thinking about how many samples we have, how many variables we have, and then try and write hypotheses, thinking again about what we talked about in the last couple of lessons is, well, what are we trying to show? And then work backwards to figure out your hypotheses. When you're done with that, hit play, and then we'll go through the answers. Okay, so let's go through these. So in question number 2, how many samples do we have and what population are they from? So if we look back up here, we actually have 2 different samples. Each group was given some Haribo gummy bears and then also some Meijer gummy bears. So we've got 2 samples, one from the Haribo population and then one from the Meijer population. How many variables are we examining and explain? So that's one variable that we're looking at, which is color. So that's a categorical variable. And then let's look at these hypotheses. So as we talked about in previous lessons, one really nice way to write your hypotheses is to look at, well, what is the question asking? They're asking, is the distribution of gummy bear color the same for each of the types of gummy bears? And then we're looking to see if we have convincing evidence of a difference. So what I did for my alternative hypothesis, this is what I'm trying to show, is that there is a difference in the color distribution for Haribo and Meijer gummy bears. So then for my null hypothesis, we're going to assume that there is no difference in the color distribution. So the color distribution or the color breakdown would be the same for both brands. All right, so now we need to figure out the expected values. So you'll notice, as we talked about in the learning targets, we're actually using a two-way table for this type of chi-square test, as opposed to the goodness of fit just gave us like a single distribution, usually in proportions or percentages. They tell you for each type how many you're looking at. But what's different here is we've got a two-way table. So we can't do the same expected counts as we did before with n times p. But what we want to do is, first of all, you should start by filling in the totals. So I write that in here, and so I'm going to say fill in totals first. So that we're just copying down from our table up above. So I filled in all of my totals, and then now I'm trying to figure out, okay, well, how many red Haribo, we'll just do this cell, how many red Haribo gummy bears should there have been? Well, what you want to do is you want to think proportionally. So I'm going to write this in the margin here. So I'm going to say think proportionally about what the expected counts would be if the distributions were the same. So think proportionally about what the expected counts would be if the distribution is the same. So in other words, if the color distribution is the same for both populations. And that's actually our null hypothesis. So in our null hypothesis, we said, okay, well, the color distribution is the same for Haribo and Meyer gummy bears, and then the alternative is we're trying to show a difference. So let's think about it this way. If it was the same for both. So for the red Haribo gummy bears, what I want to look at is, well, what if we piled everything together? How many reds were there total? Well, there were 51 red total when you combined both types of gummy bears. And altogether, there were 167 gummy bears combined. So what I'm thinking about here is, okay, well, 51 out of 167, that's about 30.5%. So 0.305. So thinking about, okay, well, if the distribution is the same, then for both the Haribo and Meyer brand, there should be about 30.5% red. So, okay, well, can we just split that up? Can I take 51 and split it in two for each of these? Well, no, because what's important here is we had different amounts of gummy bears for each. So I'm going to look down here. If I had 63 Haribo gummy bears, and we just said, well, about 30.5% of them should be red, so I'm going to multiply that by 63, and I get 19.2 about. And I'm going to like draw an arrow up here so I remember where all this came from. So 19.2 is how many I am expecting to get of the red Haribo. Well, okay, what about the Meyer brand then? Well, it's still 30.5%, but now the Meyer, there were 104 of them. So that one's going to give me 31.8. So I'm going to fill this one in right here, 31.8. Now, a really nice thing you can do to check here is, well, remember, these have to add up to 51, which they do. And if they didn't add up to 51, I would know I did something wrong. So let's try to figure out, well, where all of this came from. There's actually a shortcut formula for this. And so what I'd like you to put over here to the side is that the expected counts, well, where they're coming from is, let's look at just this, again, the red Haribo. I took the total for that row, which was 51, and I divided it by 167, and then I multiplied it by 63. Well, because of the commutative property, we could really actually just do this as row total, so that'd be the 51, times the column total, so that's the 63, divided by, I call this the table total, which is the 167. So it's just a different order, but what we have here is we're doing the 51 times 63 divided by 167, which gives us our expected counts for that cell. So what I'd like you to do is to take a few minutes and find all of the rest of the expected counts. And then when you're done, we'll look at the answers real quick and then move on to the next page. Okay, so these are all the expected counts you should have gotten. So double check all of yours. Again, when you're doing these on your own, what's super helpful is you can go ahead and add up the numbers. So add like 8.3 and 13.7 and see, okay, yes, I got 22, so I know I did it right. So always double check your totals, and that will help you to make sure you're doing everything correctly. Okay, so on to the next page. So what we're doing here then is turning everything into a full 4-step significance test. So pause the video, and I'd like you to work through this entire page. You're really just putting all the pieces together from this first page here, so a lot of the parts are already there, but then combining it with what you know from the last couple of lessons on chi-square. So take a few minutes to work through that, and then push play when you're ready to go over the answers. All right, so let's go through the 4-step. In the state portion, we've got our hypotheses. So again, just relisting what we put on the last page. So the null is that there is no difference in the color distribution for the brands, and then the alternative is that there is a distribution in the color distribution. I'm sorry, that there is a difference in the color distribution for Haribo and Meyer gummy bears. The name of this procedure, as we talked about in the learning targets, is the chi-square test for homogeneity. And then we'll check conditions. So again, it's random, 10%, and large counts. What I do want to point out here is make sure that you are checking the 10% condition for both populations, so for the Haribo gummy bears and for the Meyer gummy bears. So you do need to check it twice. On the large counts, because we already calculated all of them up here, I don't want to re-copy all them down. So what I did is I just put all expected counts greater than 5 and then showed my lowest one, which was 8.3, and that was from the green Haribo expected counts. Our specific formula is the same, so we've got our chi-square formula, and then for the work, again, I just showed the first couple of the contributors to the chi-squared and then the last one, and added everything up and got 2.93. So that is my chi-square test statistic. In order to turn that into a p-value, I need to know the degrees of freedom. And so this is a new formula for degrees of freedom because we're dealing with two-way tables instead of with chi-square goodness of fit, it's just a single distribution where we did categories -1. When you're doing a two-way table, you have rows -1, so your number of rows, or in other words, your number of categories for the rows, and then the number of categories for the columns, which in this case were like our two different samples. So we've got rows -1 times columns -1, so we have degrees of freedom of 4. So for my picture, I started my x-axis at 0 and then added on my chi-square test statistic. 2.93 is pretty close to 0, so I made sure it was clear that we aren't really far away. And then again, label chi-squared and your degrees of freedom. So for the p-value on here, remember our degrees of freedom are 4. So if I go to table C and look at 4 for my row 4 for degrees of freedom, and then move over until I find a chi-squared of 2.93, well, actually the first one is already greater than 2.93, which means my chi-square lands me somewhere over here, which is going to be greater than 0.25. So you could list your p-value as greater than 0.25, or you could also do this in your calculator. So in your calculator, you'd need to go to your distributions menu, and then you're going to do chi-square CDF. Your lower bound, so where we started shading on our picture, is right here at 2.93. And then we go up to essentially positive infinity. So I just put a large number. I usually use 10,000. And then your degrees of freedom. And that gave us a p-value of 0.57. Either answer would be accepted there. You can say greater than 0.25 or use your calculator for 0.57. So for my conclusion, because the p-value is greater than 0.05, we failed to reject the null and do not have convincing evidence that there is a difference in color distribution for Haribo and Meyer gummy bears. All right, so the last thing I want to point out is how is this test different from a chi-squared goodness of fit? And this is really coming from the number of samples in population. So for a chi-square test for homogeneity, you're looking to see, are the two populations homogeneous, meaning do they have the same distribution? So we have two samples from two different populations, whereas with a chi-squared goodness of fit, you have one sample from one population. So that's how you can tell the two apart. Additionally, the chi-square test for homogeneity uses a two-way table, which makes it easy to identify. All right, so in our important ideas, what I want to do here is I'm just going to talk about the things that are new that we need to add in. All right, so let's look at our first learning target, which was about hypotheses and expected counts. So with the hypotheses, I like to do a fill in the blank with these. So sort of a generic hypothesis that you can do with a chi-square test for homogeneity is that there is no difference in the, and then it's whatever variable we're talking about. So I'm going to put here, it is going to be a categorical variable. So like with us, it was gummy bear color. So there is no difference in that categorical variable distribution. So like gummy bear color distribution for blank. And that's whatever one, like your first population, so Haribo, and then your second population. So in our case, it would have been Meyer. And then the alternative hypothesis is the opposite of that. So that is that there is a difference in the distribution. So there is a difference in the categorical variable distribution between your two populations. All right. The second part of our learning target, which was about expected counts. So what I'm going to put here is expected counts. And this is when you have a two-way table. So when you're doing this type of chi-square test, your expected, I'm just going to abbreviate, equals, it is the row total times the column total divided by the table total. Okay. Our next learning target was about degrees of freedom. So our degrees of freedom for this type is number of rows minus 1 times the number of columns minus 1. From there, we would find our chi-square test statistic and turn it into a p-value. We already have that formula for chi-square, so I'm not going to do that again. I am going to note on here, though, about chi-CDF, that you would do the lower, upper, and then your degrees of freedom. And then everything else there is the same as previous lessons, so I'm not going to go through all that again. I do want to point out one important part, though, is about how to tell the difference. So we're going to call this will be our fourth learning target, the difference between the types of chi-square tests. So far we have chi-squared Goff, and this is one sample and one variable. A chi-square test for homogeneity has two samples, but then also one variable. So in this case, we had two samples of gummy bears, but we were analyzing the color for both of them. Whereas in the previous lesson, we had one sample of M&Ms, and we're analyzing the color for that. All right. So go ahead and read the Check Your Understanding problem and try to fill in these questions below. You're not going to do a full 4-step on this. We're just looking at expected counts and then calculating chi-squared, so not going ahead and doing the whole thing. So pause the video, fill that in, and come back when you're done. All right, so we'll start with our hypotheses. So in this case, we are looking at our two populations, would be the people who are asked by a male interviewer and by a female interviewer. And then our categorical variable is how they responded to the question. So for my hypotheses I have for my null is that there is no difference in the distribution of response to question when asked by a male or female. And then the alternative is that there is a difference in the distribution of response to question when asked by a male or female. In part B, we are just doing some of the expected counts. They've asked us to show our work for the male yes cell. So I filled that in. When you look at the total for the male column, that's 50, times the total for the yes column is 69, and then over the table total, which is 100, so we get 34.5. And then I've filled in the rest of the expected counts for all of the cells as well. And then in part C, we're just calculating the chi-square test statistic. So again, show at least a couple of the contributors and then get a total, which in this case is 4.25. All right, so that is everything you need for a chi-square test for homogeneity. Tomorrow, we're going to look at our last type of chi-square test, and that is a chi-square test for independence. It'll be very similar to what we went through today. So I will see you then.